Okay, due to some reasons, the host hasn't come. But I think we can start the presentation. Welcome to join Innovative Innovations in Digital Design webinar. And today we will have two very amazing presentations. The first presenter is Chaoyu. She's a PhD student at ETH. And Chaoyu, you can start to share your slides. Uh, you are on mute. Could you please open your microphone?
Can you see my screen?
Yes, yes. Yeah, very beautiful image. Thank you.
Thank you.
Thank you.
Hello everyone. I'm Chaoyu. I'm currently a PhD student at ETH Zurich in Architecture Technology Institute. And I want to firstly show my special thanks to IDD to invite me to share my research with you. And today my presentation is about knitted tie bolts. It's a new method to design, fabricate, and construct tie bolts. So these are the content that I'm going to show today. So why I'm focusing on structural shells and bolts, why we need new methods to think about to construct them. And in the end, I would like to share the first demonstrator, which you see here. We call it a flip. So our construction industry faces a lot of challenges, both environmentally and socially. It contributes to 40% of global CO2 emission. And to meet the Paris goal of limiting the global temperature rise to 1.5 degrees, we need to reduce the emission significantly. A major factor contributing to these emissions is the materials used in construction. Currently, the construction industry consumes about 40% of global resources and produces 30% of human waste. By 2060, these numbers are predicted to be doubled. However, we also face a challenge for new buildings. By 2050, another 2.2 billion people will be born, And 2.5 billion people will be living in cities, rising the city land area by another 141%. These changes are located mainly in the low-income countries. Facing all these challenges, along with a persistently low production growth in the construction industry, it's crucial that we consider how we should design and build structure elements for the future. Voltage structures, they are efficient because they are in pure compression and can span large spaces. The loads, the self-weight of the structure are transferred to the supports through arching action without bending. The structure form of shells and bolts can reduce the material quantities of the structure, allow for material in loads, and if they are built in discrete elements, they can be potentially disassembled and reused. A study showed that vaulted roof and floors made of earth blocks and tiles can reduce carbon emission by up to 80% compared to conventional slabs. Most of the regions where this earth architecture is prevalent are located in low-income countries, where it's the same areas where a lot of construction is expected to take place in the next decades. Additionally, these areas have a long history of using like earth blocks and tiles to build vernacular architecture. But the challenge lies still, how can we build such structures now? Because the traditional way of such construction relies on the scaffolding to support and guide the tiles or bricks, and skilled masons to place the bricks or tiles on the top, which is very labor intensive. Also, these structures are very sensitive to earthquakes. Can we find a new way to construct such structures? And I want to talk a little bit about what my PhD is, just to explain why, how flip is created. So my PhD proposes a new construction system for tie bolts using a knit restraint pneumatic formwork, which combines the pneumatic formwork to create our geometry and knitted textile to restrain the inflatable locally to specific geometry and dredges the ties on the surface. So in this system, the pneumatic can naturally form synclastic shape, which is beneficial for walls. And this simple expansion mechanism of the pneumatic can lift up the ties into the 3D space. The knit features customization and behaves in tension. It has two functions in this system. Firstly, it can stretch fully and restrain the pneumatic. And secondly, it connects and ridges ties. The knit will stay in place and improve the ductility of the voltage structure. And all these three elements make the construction method ideal for low-income countries where local materials can be used. So this is how the system works. During construction, the knit connected ties can be laid flat and anchored on the ground. And they are inflated. The knit is tensioned and restrain the pneumatic. Then the gaps are filled, and after the first layer is finished, we can add more layers on the top using human or robots. And afterwards, the pneumatic can be deflated and reused. So these are the first prototypes that I've made. Here, the knit is replaced by the 3D printed connectors using flexible materials. You can see very clearly the spacing variation between the ties here. And the connect ties, they are not developable, but can be laid more or less flat. And then they are connected to these 3D printed supports. And here I use a latex membrane to inflate. And on the right is a shell after plastering. Yeah, it looks like I have the worst plastering technique award here, but you can still see clearly like how the tile patterns are from the mirror beneath this tiny shell. So luckily, I got the chance to scale this concept up at the Digital Futures workshop. It just happened 1.5 months ago. So the content I'm presenting is really fresh today, and where we built the flip. So because of the extreme, like tight schedule, we only have roughly 2 months before the workshop starts. So instead of using air, we use gravity to define the global geometry, like what Heinz Isler did half a century ago. So due to the coupling relationship between tension and compression, we designed a hanging shell, which is composed by a hanging fabric and the ties. And then we will add a motor on top of it to rigidize it. Then we can flip it, which turns into a shell in full compression. And afterwards, we can add more layers of ties on the top, both manually or using robots or drones. So the fault finding process of this shell, we use the state-of-the-art force stamping method, which is used for designing tension membranes. So the input surface is 3 by 3 meters with a central hole. The corner vertices and vertex along the diagonal axis. So we anchor these 5 points where are the supports, and then we assign uniform force density to them and for higher force density to the boundaries. Vertical loadings were also added to simulate self-weight of the structure, and subsequently we turn the form geometry and the reaction forces at the support. Afterwards, we can materialize the geometry. So the first problem that come up with this construction method is the tiling pattern. Because we use a hanging fabric, so this method allows us to decouple the tiling pattern from the construction sequence. So instead of the mason puts the tiles or bricks one by one, now we can pre-compute this tiling pattern. Here we adopt rectangular tiles, which is most common in construction nowadays. And our goal is to minimize the unique pieces, but still assure the aesthetics of the input geometry. So instead of the state-of-the-art method, which will result in a lot of like tiles that need to be cut, we formulate this problem as a global optimization problem in 3 steps. So the input surface is firstly converted into a quad mesh using a field-guided approach, which uses an orientation field and prioritize higher distortion reduction. So this orientation field is driven by principal curvature and defined continuously over the surface. If the field is locally not smooth, a singularity will occur, resulting in an irregular vertex in the quad mesh, which in our case means an irregular tile. So here are 2 examples. So this input surface obviously non-developable, and a singularity shows up in the middle. So if you see clearly, there are a few like tiles that are overlapping here. Alternatively, we can also reduce this singularity, but as a result, we will see like the gaps are quite big in the tiling pattern. We can also optimize our quad mesh to reduce to improve the gap between the tiles, but we need to note that then the overall geometry need to sacrifice and might deviate from the input surface. Based on this quad mesh, the arrangement of rectangles can be generated by connecting pairs of adjacent faces, which is the second step, the matching. So each rectangular face represents half a tie. So to generate a rectangular tie, one face can only be connected either one time or 0 time. If it is not connected, then this 0 time, then this face represents a half tie. And we formulate this as a mixed integer programming program, and our goal is to maximize the pair of adjacent faces to generate as many ties as possible. So given a set of faces F and the possible edges E that connect adjacent faces, we want to maximize the matched edge, which is E hat. And here you can see the outcome of this optimization on a 10 by 10 grid and an 11 by 11 grid. We see there are a lot of ties that are in parallel to each other, which is not ideal. So in tie voting, the ties are often staggered to avoid continuous mortar joints. And to avoid these parallel edges, I introduce a new set of variables to describing the neighboring parallel edges and formulate them as penalties in the objective function. And you see this is the outcome on the same grid. It already looks quite feasible. And it also works on a mesh that has singularities because this optimization is purely based on topology. And other tiling patterns, such as a running bound pattern or a herringbone pattern, can also be targeted by replacing the penalty term for a parallel edges with a different term that penalizes or rewards certain combinations of edges. So you see, this is our input geometry that we showed before, and we apply a running bound pattern on top of it. And here are some more results. Afterwards, the last step is simply to generate the ties. We can use the vertices along the two connected faces to compute the best fit plan and generate the tie. The computing time for remeshing is in general less than 1 second, and the time for matching, it grows exponentially with the input size. However, this can be overcome by separating the input into small batches. And here is how the tiling pattern looks on our shell. We have two singularities. Yeah, here. And because we need to flip the shell, so we materialize it using some lightweight OSB boards with a thickness of 18 millimeter. They are cut into these wooden ties, which has a length of 194 millimeter and a width of 97 millimeter. The size of the tie, it can be also like changed based on the field that we used for the remeshing step. And these are how our ties look like. These ties, they are connected to the knitted fabric. The fabric is manufactured using CNC knitting by some polyethylene yarn, and you see that the tiling patterns, they are embedded in the knitted fabric using double jacquard knitting. So this fabric is knitted by my collaborator, Dr. Igor Liu. And the OSB ties, they are connected to the knit using staplers. The whole process of stepping the ties to the fabric takes about half a day with a group of like I think 2, 3 people, and they do shifts during this half a day. So normally a person needs to stretch the knit so the pattern will fit the tie, and then the other person staple the tie and the knit together. And on the right, you see this connected ties on the knit. The next step is to attach it to the support and the wooden frame. So the fabric and the ties, they are suspended using 5 support structures constructed in waffles, which is shown here. The waffle structures, they are made of OSB boards with a thickness of 80 millimeter. And the reaction forces in the support, they are balanced by the tension ties. You see them here. And also to prevent any shifting or like displacement during the flipping process, the 5 supports, they are anchored to the wooden frame, which you see here. The choice of the cross-section dimensions of the boundary beam is determined by the maximum bending moment of the frame, especially at the midpoint of the wooden beam. And as a result, we use white pine wood with a cross-section of 60 by 100 millimeter. And this is how the frame and the supports look like when they are on the ground. And then we need to attach the ties and the knit on the frame. So these boundary cables, which you see here, they are responsible actually to bearing all the load of the knit and ties, and they are anchored to the bottom board of the support, which we'll see more clearly like in the video. Oh, you see there's the eye bolt here, and the cables go through the support and anchored there. And then afterwards, the top board of the support can be added and screwed, which fix the knit into the correct position. Yeah, this is how it looks like. And we also add a few more screws on the support, so that when we add motor on the top of it later, our knit or our motor can be better attached to the support. Afterwards, the wooden frame can be lifted to the correct height. This is how it looks like from the bottom and from the top. The next step is to rigidize the structure. So during flipping, the truss line deviates from the design geometry, forcing the structure to rely on the tension capacity of the material. So here I did a FEA analysis to check the tensor and compression strength of the shell during flipping based on the strength method, which is often used for systemic assessment for complex bolts. So here we adopt a fast static motor in the end, which has a compression capacity of 40 megapascal after 2 hours of curing. And this is how it looks like when we try to fill the gaps. We fill the gaps between the ties and also rigidize the knit from the bottom. So the next challenge is the flipping. We flipped the shell along the middle of the frame so that we can reduce the time when the shell is in the state of a mixture of tension and compression, because this shell is stable when it's fully in tension and when it's fully in compression, but might not be that stable during in between states. So we want to reduce the time there. We firstly install the rotation axis in the middle of the frame. Then we attach some straps on it so that we can control the rotation speed and the orientation. And then we remove the corner supports and flip the shell. After the shell is flipped, the four supports are moved back. And we will see this process in the video here. And for validation of the geometric precision of the proposed method of this research, we measure the two stages, the two states of the structure. So here is the hanging shell on the motoring side, and on the right is a flipped shell on the tie side. So in general, these two states have an average of 2.5 centimeter deviation over the entire 3-meter span. And the largest deviation happens along the support in the middle and around the singularities, which you see here, where there are a lot of unique ties here. And we can already see, like in the hanging stages, that this part is not very smooth compared with the other part. And we think that these errors can be caused by the manufacturing accuracy of the knitted fabric, the slackness of the boundary cables, and the complexity of the unique ties, considering that a small number of ties, they are not CNC cut, but cut by the student on the site. And in these figures, we can also observe that the hanging geometry and the flip geometry are almost identical. And I think between these two geometries, the deviation is around, I think, 4 or 5 millimeters, so which can be ignored thinking about the tolerance. In conclusion, the flip, it's realized a 3-meter span tie bolt using knitted fabric as a formwork with extremely low budget and tight timeline. And the knit is left in the structure as reinforcement, and it successfully resists the 180 degrees of flipping, which is, when we compare it to earthquake, this is an extreme situation. And the process is proven to be not only economic, but also time efficient with little requirements of skilled laborers. because all the students involved, they don't have almost zero knowledge about construction. And this project is not only a proof of the concept of my PhD, but also proposed a new way to generate tiling patterns using this global optimization method, which I presented earlier. And so what's next? Yeah, of course, instead of using gravity, I will use air to construct boats in the future. And also my plan is that I want to look more into the structure contribution of the knit in my system. And I want to acknowledge that this research is fully funded by the Institute of Architecture Technology, ITA at ETH. And I want to deliver my special thanks to Tongji University and Digital Futures Committee for funding the clip and make it possible. Lastly, I would like to receive your questions, engage in some in-depth discussion, and explore potential collaboration together. Thank you.
Thank you, Chaoyu, for sharing the amazing work. And I have also seen like dozens of videos when the news vault was flipping that night at Digital Future in Tongji, and it was really smart and a stunning idea to design like almost perfect vaults like this in digital fabrication process. So now it's time for all. If you have any questions, like please ask here or type in the chat, so we can deliver to Chaoyu.
Yeah, exactly. Yeah, so um, in general, like inflation can create a thin plastic curvature, which is what both needed. But of course, designing an inflatable formwork is the resulting geometry is not identical to the a share in compression. So we have to do an optimization so that these two forms will match.
May I ask a question? Thank you.
Yeah.
Thank you for your amazing presentation, and I think this is a very successful project, and you implement a low-cost, material efficient, lightweight, and elegant structure. I have a question that is, did you remove the wooden framework after you flipping the structure?
Yes, sorry, I forget to mention this. Yes, so the original idea is that we want to remove this. We want to first lower the wooden frame down to the ground and remove it. But doing flipping, unfortunately, like there's a diagonal beam that collides with the scaffolding on the side, and then the screw was loose, and the result is that there's a crack at one support. And for safety issue, we didn't want to move it again, and it was still on the scaffolding and the support, and we just show this as a final state. This is really because of the safety like consideration.
Okay, thank you.
Yeah, I have I have one, maybe it's like common but not questions, because in the last page I see that if you like do further work, you might use air membrane or some like inflatable material instead of flipping, because maybe the whole vault is too heavy or something, so it's not gonna flip. But I have done some inflatable fabrications before, and sometimes if it is a sphere or some like very regular shape, we can do it. It's really easy to inflate. But if this is a really strange or like customized shape, it's kind of hard to detect whether it's like nicely inflatable or not, or it can be like there is some deviation. So do you have a process for that? Do you have thinking like how to scan it afterwards or how to examine the whole shape?
Yeah, I completely agree with you that inflatables are super sensitive to the shapes. But also, like one special thing about my construction method is that it's not like casting concrete on the top of the membrane, so it's just used as a lift up, and also the ties connected by the knit, it naturally becomes a restraint for the pneumatic, so it cannot go into like wherever it wants to be. And also I can like simply like slightly overinflate my membrane so it can like tension, like fully tension my knit and the ties. And then like a little bit deviation, it will not influence the aesthetics of the final shell and would be actually benefit for my shell because my knit is tensioned. It's like reinforcement, but it's tensioned inside before the gaps are closed.
I see, I see. Very smart. Thank you. If you have like further question, you can type in the chat or you can enter our WeChat group and ask Chaoyu after that. And thank you, Chaoyu, for sharing this. Now we're coming to Dr. Yu Li from Tongji University. So Dr. Yu Li will present a report entitled From Force to Forms, Innovative Structural Design Based on Multi-Material Topology Optimization. And let's welcome Dr. Yu Li.
Thank you. Thanks for your introduction. Wait. Wait a minute. Can you see my screen now?
Yes, thank you.
Yes.
You can start.
Thank you. Thanks for the introduction and the invitation from IDD. Hello, everyone. I'm Yuni. I come from Tongji University. I have just finished my PhD study and obtained my PhD degree from College of Architecture and Urban Planning and 2 months ago. Also, I have studied in the STEM team, which is the Center of Innovative Structures and Materials in MIT University. I have been supervised by Professor Mike Xie and Professor Fei Yuan during my PhD study. And during my PhD study, my research mainly focused on topology optimization and its application to architectural design. Especially, I have done some research about multi-material topology optimization. The title of my presentation today is From Forces to Forms, Innovative Structural Design based on multi-material topology optimization. And this is also the name of my PhD thesis. Sorry. Actually, the title was inspired by the famous book Form and Forces, Designing Efficient Expressive Structures. I think maybe some of you have read this book. It's an interesting book which presents many famous and innovative structures. I like this book very much. Here are the contents of my presentation today. First, I will introduce some concepts about topology optimization and multi-material topology optimization. Then I will illustrate the architectural design workflow based on multi-material topology optimization. Next, I will show some practical and conceptual designs based on multi-material topology optimization. Actually, there will be 3 bridges to be introduced today. In the famous book, The 10 Books on Architecture, which Ru Wells argued that every building should take into account firmness, commodity, and delight, which are regarded as the 3 essential principles of architectural design. Among them, firmness is considered as the most important principle. Structure-based architectural design, or called structured performance-based architectural design, which has been studied and practiced for a long time. Under this design concept, the architects use structured analysis techniques to assist the designing process and combine the form of buildings with the structured design. In this way, the buildings can have the structural efficiency and the elegant form at the same time. One or more reliable technical approaches is graphic statics. Starting from Archimed's research on nevers, the development of graphic statics gradually developed and matured until 19th century. Then some structural analysis or form-finding techniques emerged, like topology optimization and some other advanced techniques. Then I will illustrate some concepts of topology optimization based on ESO and BSO methods. The evolutionary structural optimization method, also known as the ESO method, was initially proposed by Emission and Steven in 1992. The principle of ESO method is very simple, which means gradually removing inefficient materials from a structure. Presented here is the topology optimization of a 2D truss subjected to a concentrated node using the ESO algorithm. After several steps of material removal, a 2-bar truss is obtained. Based on the ESO method, Yimin and his team further developed this algorithm by introducing the bidirectional evolutionary structure optimization method, which is also called the BSO method. And in this method, both the material addition and removal can occur at the same time during each iteration of the topology optimization. And the example here, presented here, demonstrates the use of BSO method for topology optimization of a cantilever under a concentrated load. I think you might have seen these famous buildings designed by using topology optimization techniques. The Riverside Building in Japan, the Shanghai Himalaya Center, the Charter International Convention Center, the Bialic Pavilion by Zaha Architects, and some other conceptual designs. However, These projects are designed based on single material topology optimization, and the single material topology optimization techniques have limitations in applying to composite structures like steel concrete structures, but which are more common in building structure. The last part is an introduction on how to extend single material topology optimization to multi-material topology optimization. We were wondering that whether we can use two different materials to compose a structure in topology optimization process. The idea is very simple. One material suitable for tension is only tensioned, and another material suitable for compression is only compressed. The two materials will perform their best mechanical performance and forming an efficient composite structural system. As for whether a material is more suitable for tension or compression, it depends on the comparison of this material's behavior and tension and compression. For instance, for concrete, it's evident that it has excellent compressive performance, but weak tensile performance. Therefore, we generally consider that concrete is more suitable for compression. As for how to judge an element in the structure is tensioned or compressed, here we use the first invariant of stress tensors as a criteria, which is the value reflects the volume change of an element. When it's larger than 0, which means that the element is enlarged in volume, and this element is regarded as tensioned. And when it's smaller than 0, it means that the element is decreased in volume, and accordingly, it can be regarded as in compression. Then there are some other assumptions about the materials. First one is the two materials of the structures should be isotropic. The last one is the two materials should able for tension and compression respectively. And the third one is the interface between the two materials should have excellent adhesion. Based on this method, the multi-material topology optimization process is illustrated as the animation. After about 100 iterations, a reasonable multi-material distribution is achieved. The steel material is mainly located in the upper region of the cantilever, responsible for tension, and the concrete is mainly distributed in the lower region of the structure, responsible for compression. The two materials form an efficient composite structure. So, what are the advantages of multi-material topology optimization compared to single material topology optimization? Here, based on the same cantilever, both single material and multi-material topology optimization are performed. In the single material topology optimization, the material needs to be both tensioned and compressed. In contrast, in the multi-material approach, two different materials, such as steel and concrete, are used for tension and compression, respectively. In this way, the multi-material approach can greatly reduce the amount of steel used. So, using the multi-material BSO method can generate efficient composite structures. Here we use this method to simulate a kind of bridge form, which is stress-driven bridge. The structure obtained by using multi-material topology optimization is very similar to the two famous rail bridges, which are named Tongji Bridge and Colorado Bridge, designed by Qin Wu and Tong Yanlin respectively. Similarly, this multi-material BSO algorithm is also applicable to 3D structures. Here, based on a 3D continuum, single material topology optimization and multi-material topology optimization are performed. It can be seen that in the single material solution, the structure is symmetric, and the steel material is allocated in both tensioned and compressed areas. Where in the multi-material solution, the structure is not symmetrical up and down, where the steel material is only in tension. In this way, about 70% of steel can be saved compared to single material solution. Well, based on the proposed multi-material BSO method, which has been published on Composite Structures Journal, we have developed the architectural design workflow based on this method. The workflow mainly includes two parts: the topology optimization section and the control method. You know that structural efficiency is not only the goal that architects pursued. They need to consider other requirements like the functionality, aesthetics, and construction costs. So we can use the control methods like refining design domain or adjusting topology optimization parameters until the architectural requirements are satisfied. Okay, let's see some cases. The first project is a pedestrian bridge over a railway. This is a collaboration between our team and the T1 company. To cross the railway, the Shenzhen government intended to build a pedestrian bridge. The conceptual design shows like this. Both the arched and the flat walkways are possible. There are three different famous of this bridge: the deck arch bridge with flat arch, the variable section PC girder bridge, and the variable dips spiral shaped PC girder bridge. Finally, we selected the last one, the variable dips spiral shaped PC girder bridge as the conceptual form. Sorry. Here is the design process based on multi-material topology optimization from a 4-square design domain to a narrow design domain. We use the two materials, steel in red and concrete in blue, to build this bridge. You can see that by refining the design domain, we can get diverse designs. And by adding a non-design domain, we can drive the direction of the topology optimization. Here, we added a central vertical column as a non-design domain, and as a result, we obtained a different design with fewer branches. Moreover, by adjusting the filter radius, we can obtain a result with even fewer branches. Here is the structural analysis of this bridge. Here are the renderings of this bridge. The second bridge is called the innovative long-span steel concrete composite bridge. This is also a collaboration between our team, T1 company, and South China University of Technology. This work has been published on Engineering Structures Journal. Here is the background. CRF bridge, or called continuous rigid frame bridge, is a kind of common bridge type, but the stiffness of CRF bridge is hard to be satisfied when the bridge spans more than 300 meters. So we set a 3-span CRF bridge as the design domain and try to find a more efficient structured form. By refining the design domain step by step, we made the structure increasingly slender and more similar to a real CRF bridge. The pictures here show a CRF bridge named Chongqing Jialin Rail Bridge under construction and the view of its completion. You can see that the symmetry of the main piers is essential to the construction of a CRF bridge. So we must find ways to make the main piers symmetrical. By setting a symmetrical region with a reasonable width, we can obtain the bridge structure with symmetrical piers. After testing, we finally choose a symmetrical region with a width of 200 meters for the following steps. Additionally, we want to explore more forms with an expanded design domain over the bridge deck. As you can see, with different expansions, the results can be completely different. We choose the last one design domain for the following processes. By adding different non-design domains, we can also obtain diverse designs. Here we added the main arches and the vertical column as the non-design domains. Besides, we have also considered the multi-load cases, like the lateral seismic loads. Finally, we choose one competitive result and perform the post-design of the bridge. The steel components are designed as steel cables, and other parts are designed as concrete components, forming an efficient composite structure system. Here are the renderings of the conceptual design: the view from the boat, the bird's view, and the view above the bridge deck. Then we have applied a trail design based on the bridge. This is a diagram showing the main components, which mainly include main girder, main pier, and lower chord arch, column on the arch, and some other components. The static analysis shows that the new bridge is quite rigid, and the gross analysis of the mid-span deflection of the main girder also indicates that this composite bridge is competitive in terms of long-term deformation. In addition, we have also performed some dynamic analysis, and the results are consistent with the static analysis. For this completely new bridge form, we have developed a feasible construction method and the workflow. There is no need for special equipment or methods to build this bridge. It can be constructed completely using currently developed construction techniques. More importantly, compared with other bridge types, such as hybrid girder CRF bridge and cable-stayed bridge with similar spans, the proposed new bridge is also competitive in terms of economical indicators, which can save at least 17% of material cost. The last project is about a light work arch bridge. This is a bridge proposed to be built over Yangtze River, and this is also a collaboration between our team and the Tianli International Company. This work has also been published on Engineering Structures Journal. This arch bridge spans 470 meters. It's a half-through arch bridge with two main arches. We have done some finding work for the local structure of this bridge. Firstly, we have designed the wind bracing by using topology optimization. Wind bracing is the key structure connecting the two inclined main arches. We want the wind bracing structurally efficient and lightweight at the same time. So we simplified the curved design surface into a flat 2D design domain and used the 2D structure. I used the 2D topology optimization to find the optimal topology with multi-node cases considered. The result shows like this. We call this new structural form variant K-shaped wind bracing. By compared with other typical wind bracings, including the K-shaped wind bracing, the S-shaped wind bracing, and the double cross-shaped wind bracing, we can say that the new variant K-shaped wind bracing is better in terms of stiffness and the stability. Besides, the new wind bracing brings about a better visual effect with a lighter and more dedicated members and a more transparent appearance. From the aesthetic comparison between the proposed bridge with the new wind bracing and the bridge with the conventional wind bracing, you can see that the proposed bridge is more slender and elegant. Besides, we have also designed the spherical bearing by using topology optimization. The spherical bearing is also an important structure in this bridge. Based on the multi-material topology optimization, the tangent and the compressed parts are identified. Finally, the spherical bearing is post-designed like this, which will be fabricated by metal casting. This is a rendering of the whole bridge, and this bridge is under construction now. To conclude my presentation, there are three small points to consider. The first one is, based on multi-material topology optimization, it's possible to achieve efficient, aesthetically pleasing, and economically cost-effective structures in the conceptual design phase of buildings. The second one is, by using multi-material topology optimization, it's possible to find innovative structural forms that are even more competitive than those designed by experienced engineers. The last one is the application of multi-material topology optimization in both practical and conceptual projects demonstrates its significant advantages in structured performance-based architectural design. Thank you all for your listening and attention. Any questions you may have are welcome.
Thank you, Dr. Yuli, for your amazing presentation and very solid knowledge. And now I know more about how to design the window bracing. And yeah, and if you have more questions, please feel free to type in the chat or directly open your mic.
I have a question. Thank you, Dr. Lee, and I think your presentation showed a lot of your work in your PhD stage, and I have a question that is about the structural performance laws. Because I remember you mentioned a lot of about you applied design domain. You changed the design domain and the applied non-design domain in your page 19 and page 29, page 30. Have you compared the performance the compliance between the original topology optimization and and the new design after changing design domain and non-design domain?
Thank you, Albert. Thanks for your question. Sure. We have used many methods like refining the domain and changing the parameters to obtain diverse designs. The purpose is that you know that in the design process, architects usually want to have the structures that not only satisfy the structural efficiency, but also need to consider other aspects like functionality and cost something. So we need to control the failure topology to satisfy these requirements. So we use many methods to obtain diverse design. Actually, you mentioned that the new results usually have lower structural efficiency compared to the optimal structure, which is not effective, not influenced by this method. Yes, you are right. Actually, these researches and these studies have been performed by many researchers. There are many researchers like our members in the CISM team have done these researches. So I don't think this is the main focus of my study. So I just set their researches, but don't research these aspects in details.
Okay, thank you for your answer.
Thank you.
If we don't have like more questions, we can stop right here. And thank you, Dr. Yu Li, for your amazing presentation. And if you have other questions, please feel free to join the WeChat group. Or if you're watching the live streaming on YouTube or Bilibili, please feel free to contact the author directly via the email. They're already like read it in the presentation. And we are highly encouraged to any young designers and scholars to also share your work by the Innovations in Design, digital design platform, the IDD website. And we aim for IDD webinar, we aim to explore the nature and future of design by showcasing the outstanding work of young designers and scholars from all over the world. And IDD operates once per month, offering oral presentations and discussions in English. All recordings will uploaded to YouTube and Bilibili and available for free to all. And thank you once again to attending today's lecture. Bye-bye.